Hello again. This video covers section 7.2, which is Introduction to Polynomial Functions. We're going to cover a variety of topics that have to do with graphing polynomial functions, starting with the end behavior. To analyze polynomial functions with multiple terms, one important characteristic is the end behavior of the function. This is what general direction does the function follow as x approaches infinity or negative infinity. There is some notation for infinite behavior of y equals f of x. X arrow infinity means x approaches infinity. That is, x becomes infinitely large in the positive direction. And I like to tell my students to think about it as what is happening on the right side. And I also like to tell them the end behavior is talking about the arrows. Okay, for x approaches negative infinity, x becomes infinitely large in the negative direction. Graphically, we'll be talking about the left side of the graph, or the arrow. And then f of x approaches infinity would mean that the y values become infinitely large in the positive direction, as f of x approaches negative infinity says that the y values become infinitely large in the negative direction. And they give you some examples. So for a polynomial, and this is just fancy notation for polynomial, we can observe the general direction of the function follows by looking at the leading term a n x n. So if a sub n x is even, if it's an even power, and then what happens is on the left and on the right, it rises. So as x approaches negative infinity, f of x is approaching infinity. As x approaches positive infinity, f of x is also approaching infinity. So I like to tell my students to think about positive x squared and how that graph looks like this. On the left, it's rising, and on the right, it's rising. Okay, so what happens if it's negative and it's even? So really, there's like a big block here, right? So this is dealing with even functions. An example would be negative x squared. Negative x squared would flip over, and on the left it would fall, and on the right it would fall. So as x approaches negative infinity, f of x will be approaching negative infinity. As x approaches infinity, f of x approaches negative infinity. All right, so what happens when it's odd? If the function is odd and positive, such as x cubed, which looks like this, then on the left it will fall, and on the right it will rise, which means on the left it is going down, so it's approaching negative infinity. On the right, which is saying that x is going towards infinity, f of x is also going towards infinity. And then the last thing that can happen is if you have negative odd power, then it would flip like this. And on the left it would rise, and on the right it would fall. So this is really just fancy for saying that on the left, as x approaches negative infinity, which is going towards the left, our y values, remember f of x is referring to our y values, are approaching infinity. And you can see in my graph here that it's going up. As x approaches infinity, f of x is approaching negative infinity, which refers to the arrow pointing down. Okay, I know that's a lot of words, so let's put it into examples, because I think when we have examples, that's probably going to help to understand it better. All right, it says use the leading term to determine the end behavior of the function. So I'm going to highlight the leading term. Now, it's not the leading term because it appears first. It's the leading term because the highest degree is 5. So since it's x to the 5th that I'm looking at, it is positive because there's not a negative in front, and it is odd because the degree is 5. So what happens is on the left, our graph will go down, and on the right, our graph will go up or rise. Okay, for this next one, I have 1, 2, 3. Okay, so when we count the degree, So the degree over here was 5 because the highest one is the winner, right? But over here, this is not, it's in factored form. Since it's in factored form, I want to count how many x's there are. So that's going to really give me a negative 2x to the 4th. If I multiply that all out, I count this as 1, and that's 3, so that's how I get 4, and then the negative 2 would just drop. So what does that mean? Well, that means it's negative, and it's even. So negative even will fall into this category here. So on the left, it will fall or go down, and on the right, it will rise or be pointing up. I'm sorry, on the right, it will be going down as well, since it's negative even. So all negative even polynomials will have that type of end behavior. Okay. So now we're going to move into something else, but don't worry because we talk more about the end behavior a little later on. Okay, so the other thing that we're going to talk about is finding the zeros of the function. So there is a definition that's going to help us. It says the values of x in the domain of f for which f of x are equals 0 are called zeros of the function. These are the real solutions or roots of the equation f of x equals 0. And they correspond to the x-intercepts of the graph y equals f of x, which we've also seen to be true in our study of quadratics, right? And a quadratic is a polynomial. So what we learned about quadratic still applies here. Okay, so we can take this, if we're going to find the zeros, we're just going to set this equal to 0. And I have a feeling that we're going to get to do factor by grouping, right? So that doesn't go away. So the first two terms have an x squared in common, and I would be left with x minus 5. And then my second two terms have a 16 in common, but since that's a negative, I'm going to take out a negative 16, and I'll be left with x minus 5. This is a match, so I factor that out. And so now that I have my factors, I can set each piece equal to 0. So I set x minus 5 equal to 0, and I get 5. And then I set x squared minus 16 equal to 0. And I get plus or minus the square root of 4. And so I have 3 zeros. I have 5, negative 4, and positive 4. And graphically, that's where they would cross the x-axis. And we're going to be talking about that very soon as well. Okay, so another thing that we are going to talk about is that if a polynomial function has a factor x minus c that appears exactly k times, then c is a zero of multiplicity k. Okay, let me explain. This is already factored, which is great. So we want to determine the zeros and the multiplicities for that. So what I'm going to do is I'm going to set each, sorry. I'm going to set each term equal to, each factor equal to 0, okay? Use different colors. All right, so I set the 8x equal to 0, and I get 0. All right, so x equals 0. And since I only had that one time, I would say that that's a multiplicity of 1. All right, then I set x minus 1 equal to 0, and I get 1. But since it's squared, I can say that this has a multiplicity of 2. Then I set this equal to 0, which would give me negative 3. But since this is to the third power, I could say that this has a multiplicity of 3. All right, so that's how we find multiplicities. Okay, now what we're going to talk about is what effect do multiplicities of the zeros have on the graph. Note how the lead term changes, okay? And unfortunately, it looks like one of our little graphs got taken away, which is kind of sad. Oh no, it's like it's all messed up. Okay, sorry about that. I had to redraw the graphs for you. Wonderful. Okay, now we can get started. Okay, so in this graph, there is a 0 at 0, There's also a 0 at 1, and there's a 0 at -3, right? And this polynomial has a degree of 3, and it's positive. So on the left it falls, and on the right it rises. Okay, and then what happens is, for it to be a 0, the graph has to go through the zeros, right? Because it has to cross the x-axis to be a 0. So that's the general shape we get. But if you look at the second one up here, you can see that we have a multiplicity at that spot, at that negative, at the x minus 1 spot. And that gives us a 0 at 1. So when we have a multiplicity of 2, so that shows a multiplicity of 2, it just barely touches the x-axis and then it goes back up. So the reason why this is a multiplicity of 2 is because of the squared right here, and it happens to be at 1, it just barely touches. You can see that the 0 at 0 it goes through, and then of course the 0 at -3 it goes all the way through. Now let's look at what happens with this last example. So we have a 0 at 0, which is right here. See how it's crossing? We have a 0 at +1, which is right there. It's crossing. And then we have a multiplicity of 2 at x equals -3. So if you notice at -3, it just barely touches. It's like, they like to call it like a kiss. It just barely touches and it goes back up. So that is what our multiplicities look like with those. So we're going to talk about what happens though in the difference between the even and odd multiplicities. Okay, so there it says, if C is a 0 of odd multiplicity, then the graph crosses the x-axis at that place, at C. However, if C is a 0 of even multiplicity, then the graph touches the x-axis at C. It's still considered a 0 or an x-intercept. It's just going to barely touch if it's even. Okay, so here's an example where it says, given that f of x is equal to -3x squared times x plus 4 times x minus 3 cubed, identify the zeros of the function and whether there is a cross point or a touch point at each 0. Okay, so let's start with the -3x squared. When I plug -3x, or when I set it equal to 0, because all of these I set equal to 0 to find the zeros, right? So that would be my first step, right? I set each of these equal to 0. When I solve this, I divide by -3, I take the square root, I get 0. But since there is a squared, I actually say that this is a multiplicity of 2, and that means it just touches. So at x equals 0, it's a multiplicity of 2, it's just going to touch. And then here, I get a 0 at -4, and it's a multiplicity of 1, which is even, so it crosses. Okay, and then right here, I end up with 7 with a multiplicity of 3. And since it's odd, it crosses. Okay, so that's how I do that. That's how I figure that out. All right, now to sketch a polynomial function, we're going to follow all of these steps. But I also want you to know that when you do this for homework or on your test, you are using the really nice feature to help you graph it. So even though it's great to do this by hand, and I want you to know how to analyze the graph, I don't want you to get too hung up on making it a perfect graph. It is very difficult to make a perfect graph as a human being, whereas our calculator or our computer can make a really a better graph, all right? So we're going to start with this one here, and we're going to talk about the general shape of what this is going to look like. And when we say general shape, I really want to talk about the end behavior. So we're going to have 1, 2, 3, 4. So this counts as 2. This is 1 and 1. I'm counting the x's, right? So my degree is 4. and it's positive because it's not negative here, which means on the left it will rise and on the right it will rise. Okay, so we're going to keep that in mind, that on the left it should rise and on the right it should rise. Now for my terms, I'll have at most 3, and that's because there are 3 different factors. 1, 2, 3, right? So at most I'll have 3. And then for my intercepts, I can find the intercepts, of course, by finding my zeros, right? And I can label them as cross or touch. So for my intercept, I'm going to go ahead and plug. I'm going to find f at 0. So I'm going to plug 0 in. And this will help me to find the y-intercept. So when I plug in 0 and I calculate this, I basically end up with 1 times 3 times 4, which is 12. Negative 12, sorry, that's negative 4. Okay, so at 0, negative 12 is a y-intercept. Okay, and then I can find my x-intercepts, and I'm going to say if it crosses or touches. All right, so I set this one equal to 0. I get 1. So x equals 1, and it will just touch because it's a multiplicity of 2 because of the squared. I set this piece equal to 0, and I get negative 3. It will cross because that is just to the first power, right? It's just one of our zeros. And then I set this one equal, and I get 4, which will also cross. All right, so I like to start at the left. My farthest left 0 is negative 3, so I'm going to put a ordered pair here. I can go ahead and plot 1 and 4. 1 and 4 here. And I know that it's going to, this is where I'm going to use the end behavior to help me. So I know on the left it's going to rise and on the right it's going to rise. So what I'm going to do is I'm going to go ahead and draw that end behavior. All right, so on the left I should rise, on the right I should rise. Okay, and then I know that at 1 I should just barely touch. So I'm going to go through this ordered pair, down, back up, barely touch, down, go up. Okay, now doesn't have to be perfect. My lines don't look that great, but really it would be the curves would be smooth is what I'm trying to say. Okay, so just do your best to at least know where it crosses the x-axis and then also the end behavior. But as far as drawing a perfect graph, you don't have to worry about that, I promise. Okay, let's keep going. We've got, looks like one more here that we're going to sketch. We're just sketching, so like I said, please don't get hung up on making it perfect. Okay, so this is negative, and then we have 1, and this is 2, so that's 3. So it's negative, and the degree is 3, which is odd. So if it's negative odd, then on the left, it's going to rise, and on the right, it's going to fall. Okay, so that's just going to help me to sketch my graph. Okay, so that's what we call the end behavior that we were talking about at the very beginning. I know that this is what's going to happen to my graph. Now, the other thing I need to do is I need to find the zeros. And I end up with positive 3 and negative 1. And I know that I have a multiplicity of 2. So it's going to touch, not cross, whereas this one's going to cross. All right, so at negative 1, I'm going to put my ordered pair, and I'm also going to put ordered pair at 3 because I know that's going to happen. And all right, and then I'm going to show my end behavior. So I know on the left I'm supposed to rise, so I'm going to go ahead and draw like an up arrow. And I know on the right I'm supposed to fall, so I'm going to draw a down arrow. And I also know that on the right at 3 I can only touch, right? So I'm going to go down, through, back up. All right, so that's just a general idea of what that graph would look like. Okay, I hope this video helps, and I hope you have a wonderful day. Bye.